Okay, we need to talk about what's actually going on as we're solving these polynomials. What's the purpose of it? It's important that we understand how to solve a polynomial because there are many things in business, in science, in astronomy, in various aspects of life that are modeled by complicated polynomial equations. Do typical people like you and I go and model them? Not necessarily, but it's important that you understand that business decisions and places like NASA and schools and recruiting and all these different things are actually worked out with very complicated mathematical models because it's millions of dollars that they're investing. So they're not just going to say, oh, I think it'd be cool to put a Walmart over there. They're going to sit down with the demographics, the past history of spending, the anticipated growth patterns. They put together very complicated mathematical models. Now, they put them on computers. They don't necessarily do them by hand. But it's important that we understand just the general idea of what's going on behind the scenes. So that's why there's so much of this polynomial modeling that's fairly complicated that's in this course. Just want you to think about that. Now, we've been adding, subtracting, multiplying, dividing. What is the point of this? At some point we're getting to solving these polynomials. The way we solve them is by finding their factors, and we use division to do that. That's why you had to learn how to do polynomial division. So the vocabulary that we're going to use for this is understanding that the solution of a function is the same thing as the zero of a function is the same thing as the root of a function. Okay? All of these things mean the same thing, and what they mean is the value of x when y equals 0. Okay? The x-intercept. That's not the same as the y-intercept that we think about when we think about a linear equation. Now we're talking about the x-intercept when y equals 0. So the reason that we put those equations in standard form, where we put them in descending exponent order equals 0, is because at some point we're going to factor them and find them. Now, what does a 0 look like? This, if I have now, I've drawn a graph over here that has 3 zeros or 3 roots. The parts marked with an X are the zeros or the roots. You can see that's where the y, the up and down value, equals 0. Okay? So there are 3 spots on that graph where y equals 0. And let's say if they were -1, -3, and 2, I could put 3 binomial expressions together and multiply them like we're doing in class and find a polynomial expression for that graph or for that situation that I'm modeling. Okay? This must be at least a cubic because I see it has 3 solutions. It must be an x to the third, or it could even be higher. It doesn't have any more roots, but there could be other strange things that happen, and when we get to those kind of graphs, then we'll talk about other kinds of roots. But for now, I want you to know that when I talk about roots or zeros, this is what I mean. This is what we are trying to find. Now, where are these guys hiding? They're hiding in the factored form. So if I had an equation that was x squared plus 4x plus 3, we would use our quadratic skills from Algebra 1 and say, well, 3, the factors of 3 are 3 and 1. So I check, can 3 plus 1 equal 4? Yes. So this must have started life as x plus 3, x plus 1. This is factored form in the binomials in parentheses. What factored form tells us is the opposite sign of the zeros. Factored form is extremely important. So the zeros of this equation are -3 and -1. And so it would look like this if this were at -3 and this were -1. It's a squared, so I know that it is a parabola as a quadratic, and it has a positive, so I know it's going up. We'll have a day that we review how to find the graphs of those quadratics that you learned in Algebra 1. But for now, I want you to think about what does this mean in terms of this. That's the zeros, that's the roots. So the purpose of all that factoring is it tells us the solution to the equation. It gives us those spots on the graph. So the problem is when we get this big, crazy polynomial, we can't just do a quick factor. Quadratics are easy because they only had 2 numbers that multiplied to get that, and 2 numbers that added together to get that middle term. Now I have 1, 2, 3, 4, 5 things going on. To the 4th degree, that means there were 4 binomial expressions that I must have multiplied together to get this number. I can't just look at it and do it. So I can tell you that it actually comes out to x plus 2, x minus 2, x minus 5, and x minus 1. But the reason I can tell you that is because I started with these and multiplied it to get the number. not because I can look at it even as a teacher and glance at it and know exactly what it is. So, because this is its factored form, I know the zeros are -2, +2, +5, don't know why I put a -5 in there, we'll worry about that in a minute, and +1. Okay, so it would be a big 1, 2, 3, 4 zeros shown on that graph. Now, do not be freaked out here. I want you to think, this is on here to show you the process. We'll be spending a lot of time working through this process. But I put the same equation up here at the top. And then I decided, a lot of times what will happen is someone will give you, they'll say the first factor is x minus 4. So you know 4 is a factor. You can divide by that and keep going farther and farther down until you can find all the factors. In this case, I didn't necessarily give you that. But I look at the number 20. And remember, the constant is formed by multiplying each of the constant terms in the binomial. So I know I had 4 numbers multiplied together and they equal 20. I know that one of them had to be 5. Okay? Even I might have had, even if it was 10, it was 5 times 2. Okay? So I'm going to try 5 as one of my factors. So I put a 5 over here and I bring down my coefficients, 1, 4, -9, -16, and 20. Drop the 1 down. 1 times 5 is 5. Add them up and get a 9. 9 times 5 is 45. Add them up and get 36. 36 times 5 is 180. And at this point I say, you know, there's a problem here. Because when I multiply 166 times 5, it's going to be 600 and something. The only way this is a factor is if I have a -20 over here to cancel out my 20 and I get a 0. If I don't get a 0, it's not a factor. So I'm going to abandon this right here before I even multiply by 166 times 5 because I know it's not -20. So I say, no, apparently 5 is not a factor. But how about -5? So let's come here to -5 and I get, bring down my coefficients again, bring the 1. 1 times -5 is -5. Add them and get a -1. -1 times -5 is +5. Add them and get -4. -4 times -5 is +20. Add them and get a 4. 4 times -5 is -20. Now you see what happened here? 20 plus -20 is 0. This is a factor. It says -5, so x plus 5 is the factor. And more importantly, this is my new equation. And I put it back with x's just so you can see it. X to the third minus x squared minus 4x plus 4. Okay? I put that in, and now I say, well, I multiplied 3 things together to get 4. I have a pretty good idea. It's probably like 2 and 2 and 1, right? Otherwise, how can I get a 4? It could be 4 and 1 and 1, like -1 and +1. But let's see. To get that, I'm going to try a 2, because 2 makes sense that it might have gotten multiplied to get a 4. So I bring it back to coefficients. 1, -1, -4, and 4. Drop the 1 and multiply 1 times 2 is 2. Add straight down and get a 1. 1 times 2 is 2. Add straight down and get -2. -2 times 2 is -4. 4 plus -4 is 0. Okay? So now I know another one of my factors is x minus 2. Because remember, in synthetic, we're always going to be doing a minus of what's here. So I have an x plus 5 and an x minus 2. And what's left? X squared minus, x squared plus x minus 2. And often when you get to a quadratic, you can just stop right there and factor it. What do I have to have 2? 1 and 2. And can I figure out which one's positive and which one's negative to get a positive x? And I can. So that's how I would finish it. So the steps are sometimes trial and error, okay? But the better that you can get at synthetic division, the faster this process is going to go. And the more that you can understand that we can't always tell which one's positive and which one's negative before we start our multiplication process. So sometimes one won't work and you'll say, I was sure it was a 5. Oh wait, it could have been a -5. So be prepared for that. When you come to class, we will be spending a couple of days just working through these problems because, again, our goal is to find all of the factors of these complicated polynomials. That's the solution to the equations.